Eric Burgess here, and we have a whole bunch of series, and we want to know, do they converge, do they diverge, and if they converge, what do they converge to? Now, this is earlier in the chapter, so these are pretty much only geometric series and series that diverge. If you're looking for something that's got a little more variation, let's go ahead and just dive right in. None of these are extremely challenging. You just got to kind of know the rules of the game. So looking at this first one, whenever you're given something like this, well, try taking the limit. Because if there's something left over from the limit, if the limit isn't 0, then this thing diverges, and then we can just, move on. So let's just see right now, if we take the limit, because this looks like something that's going to have a non-zero limit, we're going to have k going to infinity. If we got k squared, let's just divide that out. So we're going to get 1 minus 2 over k plus 5 over k squared. Right, just divide everything by k squared. We were doing that earlier. If we take the limit, we're going to get 1 over 1. These terms go to 0. This is equal to 1. And we know from the test for divergence that this diverges by test for divergence. And so that is our first answer. So pretty nice. If it's 0, you can't say it converges or diverges. It's 0 doesn't really tell you anything. But if it's not 0, if it's 1, then, we've got something to say here. So that's what we have going on right there. Let's go ahead and move along here. So for this next one, looking at this, we've got two geometric series, right? We have the common ratio r, and we need to know the initial term, which we can find by just plugging in our first n. So when n is 1, this thing becomes negative 0.2. So a is equal to negative 0.2. And when n is 1 for this one, this thing has an a, n is 0. Well, not n is 0, n is 1. This becomes 0. And so this makes this 0.6 to the 0, which makes a equal to 1, right? Because anything raised to the 0 power is 1. And then we know from the limit laws, theorem 8, if you're following along in class, that we can just do these individually and add them together. So let's go ahead and do that. So the first one's going to be, and recall that for the geometric series, it's a over 1 minus r is the sum. So we just put negative 0.2 over 1 minus negative 0.2 plus, courtesy of theorem 8, we've got a is 1 over 1 minus 0.6. And let's go ahead and type this in real quick. So we've got negative 0.2 over 1 minus negative 0.2 plus 1 over 1 minus 0.6. And I get an answer of 7/3. And this obviously converges. This is a geometric series. And so that's the shebang with that one right there. All right, moving right along here. We're given another one. In this case, this looks kind of gross, right? Because it's all being crammed into one fraction. And I know it seems tempting, but you can't factor the n out like that because there is an addition sign here. So what we actually have to do is we have to take this and break it into pieces, right? Because we can go 2 over e to the n, right? Just take this piece, we can do that, and add it to this piece. Again, courtesy of theorem 8. So we have 4 over e raised to the n. And we know that n is 1, goes to infinity, all that good stuff. So here, again, we've got a pretty clear geometric series. But look at this. This r, is that r less than 1? Let's find out. So we've got 2 over e, which should be less than 1 because e is bigger than 2. And I get out 0.735, la 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 la. So this is less than 1. So this checks out. Totally okay. Less than 1, this is going to converge. This one though, well, let's see. What is the absolute value of r doing here? Well, this is 4 over e, and this is going to give us a value that's not, it's 1.47. So this is going to be greater than 1. So this is a frowny face. It diverges. So the whole thing has to diverge. And the reason is, think about this. If this is going to converge to a specific number and this is just never going to stop growing, well then the answer's got to be divergent. It's just never going to stop growing. This is going to overwhelm this piece. That's why it's divergent. All right. Next one. So we've got here another case of something raised to the n. And just looking at this, we say, well, look at this. When this goes to infinity, it's going to be 0, and we're going to be left with something over it. So it looks like a clear case of a limit law. So if we just take the limit, or not a limit law, but if we just take the limit, we're doing a test for divergence. So n goes to infinity of this thing, 1 over 1 plus 2/3 n. We're going to get 1 over 1, which is 1. Therefore, it diverges by test for divergence. Because there's something left over. There's always going to be something more to add. So that's that one. And then finally, we're left with this one. Now, this one, again, looks like a clear case of a geometric series. However, just being a bit careful, notice that this is negative. So we can rewrite this in a way that makes this a little more clear. Because you might be looking at this and going, the square root of 2 is definitely bigger than 1. It's a trap. I'm telling you it's a trap, because you'll think that r is greater than 1, therefore it diverges. But that is in fact not the case, because there's a negative here. So we can rewrite this another way. And we'll go k equals 0 to infinity. If we make this k positive, that's the same thing as taking what's inside and putting it under 1. And now this r is less than 1. 1 over the square root of 2 is like 0.707 or thereabouts. You're going to see this number a lot, by the way, if you go into engineering. At least I could speak for electrical engineering. It pops up left, right, and center. So let's go ahead and take this limit. So this, since this is a geometric series, well, if we take our first term, which starts at k equals 0, well, k equals 0, this is 0, so our r is equal to 1. So that means that, or a, my apologies, a is equal to 1. This is r. And we already know the formula, so we can do 1 over 1 minus 1 over rad 2. Because 1 was a and r is 1 over rad 2. We're going to get, we do 1 over 1 minus 1 over the square root of 2. And we get out 2 plus the square root of 2. Or if you want to write decimals, you can, 3.14. Ish. I know. So math official. And that's it. So there you go. There's a bunch of series and just how we kind of deal with them. So just a couple like kind of takeaways from doing these is we notice that, hey, for these, taking a limit never really hurts, especially if you can do it just by kind of staring at it. Like these are easy limits to take. And you say, oh, this diverges, not 0. Over here, the tricky one with this one was that the fact that we had to find a, and a for this first one was not 1, and that can throw some people off. So just plug in your first term to get the initial term a, and that'll kind of solve that, because the n minus 1 versus n can be kind of confusing. Over here again, limit law, this time it came from breaking up the fractions and doing them individually. And then we got another easy limit, and so we just decided to go with that. And this last one tried to trick us with something that was bigger than 1, but we noticed that the exponent is negative, and so we know that we can flip the inside, and that changes it to fit the criteria r is less than 1, and so we're able to quickly take the limit and find the sum using the geometric series formula. And that's it. If you have any questions, feel free to let me know. Subscribe and hit that bell icon for future videos, and we'll catch you in the next problem.